We're going to look today at benzene. Benzene is a chemical with the formula C6H6, and we're going to look in particular at the work that Friedrich August Kekule did on benzene. Now, he's been treated a little bit unfairly by textbooks recently, because actually this is what you need to know is about why he was wrong, but he was actually a very clever guy. If you just pause the video, you can work out some structures of C6H6 with the correct number of bonds per carbon atom and hydrogen atom. You'll see that actually what this molecule is not a simple problem. So here are some ideas that I have had. So we've got lots of weird and wonderful chains. We've got a really odd thing down there, but the problem is that there doesn't seem to be enough hydrogen atoms for this, and so Kekule came up with this structure here, which will be familiar from your textbook. And actually this does explain a lot about the chemistry of benzene. We will come back to this structure, and we will use this structure to explain why certain things happen in reactions of benzene. It is a good model, but the problem is it's not correct. It's one of those times in science where we have a model which works for some things but doesn't work for others, and so we need to improve that model over time. So why do we now consider this a failure? Well, it's to do with three predictions that you could make about the chemistry of benzene. If we look here, we have 3 double carbon-carbon bonds, and if you know anything about your AS, which you should know, you know that when you bring bromine into the close proximity with a double carbon-carbon bond, you will get a reaction. So for example, if we take cyclohexene here and we react it with bromine, we will end up with an addition reaction where the double carbon-carbon bond breaks, and we add the bromine over the double bond, one each side. And you will see that in a test tube, because you will take your orange bromine water, you'll mix it together with your cyclohexene, and you'll find that both the organic and the aqueous layer will be colourless. On the other hand, if you take benzene, and Kekule's benzene, you should see that actually we've got 3 carbon-carbon bonds there. We should still add bromine, and what we should have is a molecule which ends up looking a bit like this. And the trouble with that is that when we do take benzene and we do add bromine water, what we find is actually the bromine water stays orange. There's no discoloration, which means the bromine hasn't been used up. And the conclusion we can come to there is that this doesn't happen. Okay, so this is a problem, because if that was true, then this should happen. A second really important piece of evidence for the structure not being correct is working out the enthalpy change of reaction. And if we take the enthalpy change of hydrogenation and we work it out for cyclohexene again, we should have an exothermic value of minus 120 kilojoules per mole. Now, if you had 3 times the carbon-carbon bonds as Kekule's benzene does, you would need 3 times the hydrogen, which is true, we do. But what you'd find is that you would predict 3 times this. And so we would end up with a predicted value of 360 kilojoules per mole. So if we look at this on a diagram, we find that we have an enthalpy change which looks a little bit like this. We are predicting an enthalpy change of minus 360 kilojoules per mole. But when we actually do the experiment, we find that that's not true. We actually find that we have a value of minus 208 kilojoules per mole, which is less. So if we draw that on here, we know that cyclohexane is at this energy level. It's this one that we're not sure of the structure on, so we're going to assume that this is in the same place. We have less of a change there. minus 208 kilojoules per mole. And that means that real benzene, the structure of real benzene, is actually slightly more stable than Kekule thought. It's at a lower energy level than he thought, so it's more stable than his structure would suggest from its 3 double bonds. And the word we're looking for in the exams here is that the enthalpy change of hydrogenation is less exothermic than we would have expected. And there are lots of ways that people try to describe it, but the one that you should use is that the enthalpy change is less exothermic. The third piece of evidence I want to look at is something called X-ray diffraction. Now, X-ray diffraction was relatively new, and benzene was examined in 1929. So this is several years after Kekule's structure was first envisaged in 1865. So this is quite a long time has passed here, and technology has moved on. So this data became available, and they looked at the structure of benzene using this technique. And basically works by diffraction. Now, I know that X-rays are transverse waves as opposed to longitudinal waves, but it's harder to draw it that way. So I'm going to draw using longitudinal waves, and you'll have to forgive me for that. But you'll know from GCSE that if waves hit a wall with a slit in, we get a phenomenon called diffraction. In other words, the waves kind of hit the slit, and we get them going off in all sorts of directions after they've gone past the gap. Now, if you want to look at the gap between atoms, you need X-rays. Visible light just won't cut it, and that's because there's a relationship between the wavelength of the wave and the size of the gap. And what we're trying to do here is we're trying to get the gap between individual atoms. So what we're going to do is we're going to take our atoms, we're going to put them in the path of some X-rays, and we're going to then put a detector on the other side. So depending on the spacing of the atoms here, we get different results here, and that's really all you need to know about it. But you can look it up on Wikipedia. It's a thrilling read. But what this leads to is the final piece of evidence about Kekule's structure. And why it wasn't right, because actually, if you know the length of a CC single bond, which is 0.153 nanometers, and you know the length of a CC double bond, which is 0.134 nanometers, then you can draw out benzene like this. These are shorter than those. I've exaggerated it. But Kekule's structure is actually a perfect hexagon, we found, with X-ray diffraction, with a bond length of 0.139 nanometers. Now that's kind of where I want to leave it, but the question, of course, then is, well, what is this? What does that actually look like? How is it actually bonded together? And the answer is, well, we have something different happening to normal single and double bonds. How do we know? Well, because this bond length doesn't match either of them. How do we know that it's not quite as we would expect normal bonding to work? Well, because the enthalpy change evidence shows us that we have a more stable molecule than we usually would expect. And so what we've got to do is we've got to look back to the theory of how atoms bond together. So if we look at a benzene molecule like this, we have a carbon atom here, 6 carbon atoms, 120 degrees. That was shown to be correct with X-ray diffraction. 1 hydrogen atom per carbon, that works. Well, what's left over? If you remember your double carbon bonds, you'll remember that actually they're formed by 2 p orbitals overlapping. So you have the sideways overlap of p orbitals. And if we say, right, okay, well, there was a double bond here in Kekule's structure, so there must have been 2 p orbitals like that. And there was a double bond here, so there must be 2 p orbitals like this. And then there was a double bond here. there are 2 p orbitals like this. And you can see that actually all these p orbitals, these 6 p orbitals, they have an electron there each. But actually, if these 2 overlap sideways, well, surely these 2 could overlap sideways, and these 2 could overlap sideways, and these 2 could overlap sideways, and these. So why couldn't they all overlap sideways? And that is our current model of benzene. It's the sideways overlap of these p orbitals to form a ring above and below the plane, which contain the electrons which aren't bonded in our normal sigma bonds. They are contained in this new pi system. And because these electrons are free to move around the entire system, the word that we're going to use for that is delocalized. The delocalized electrons are in the pi system. Now this diagram is quite important, and it quite often comes up on an exam, so let's just complete it. This is a sigma bond that you've come across in AS. These are the p orbitals. We have delocalized electrons in a pi system, and we have that because there is a sideways overlap of p orbitals. More on that in future, but for now, Kekule's benzene is busted.